Okay? So a positive pressure basically means the water's above it and it's going to be moving towards it. So it's a gravitational pull. It's going down. Okay? Now if this is my interesting point and the water happens to be here versus here, if the water's here, it's going to be coming down, positive pressure, coming down, gravity. If this is the point that I'm interested in, wherever, and my water's here, you have a pressure that's pulling up. So it's a negative pressure. Does that make sense? To give you sort of a concept of what this table looks like. Now, the one problem with using that memory sort of device is that with matrix potential, with negative potential, this negative potential could actually be up here. The water could be here, and it could be pulled downward. Okay? And that's why we get this kind of table where we always see this sort of infiltration flow chart, and it always looks like this. That's because that initial phase is the water. Here's my soil surface. Okay? Here's my reference point. Okay? This is where I'm measuring the water. Okay? Or we can make it really simple. We'll just look at right there. Okay? How fast is that water? I put a well here, a dam. I pour water into it. Okay? And I watch how fast that water disappears. Okay? Well, what's moving that water? Gravity's moving it down. But if this soil is dry, matrix potential is also moving it down, even though matrix potential is a negative pressure. Okay? Gravity always flows that way. But matrix potential can go any way. Remember my sponge? My sponge is wet here and it's dry here. The water is going to migrate this way. It's not going to be going up or down. It's going to be going sideways. And if my sponge is like this and it's wet down here, it will go up. If I flip it all the way around and the wet's wet up here, which way is the water going to be going? It's going to be down. So you have to remember that this potential can go any direction. And that's why we get this classic infiltration curve where this is the rate, this is high, and this is low rate, okay, and this is time. Right? Well, this component from here, this rate part, is a combination of the gravitational pull. Yes, it's being pulled down, but it's also the psi matrix. It's being sucked in. Okay, until this negative potential is satisfied, at which point, from here over, it's just gravity. Does that make sense? Okay, and I think that the best way is sort of visualize where you want the water to go and where is it. Okay, if it's down here, it's going to be pulled up. It's a negative pressure. If it's up here, it's going to be coming down. It's going to be pulled by gravity. It's going to be positive pressure. Okay, so far this semester, we've basically been talking about individual particles or individual parts of the soil. We talked about that soil volume. Okay, we started by talking about the solid part, texture, structure, bulk density, that kind of stuff. Okay, and then we moved into soil water and soil air, where we're talking about the pore space. Okay, is that right? Okay, today we're actually going to start talking about the whole system. And to do that, we're going to actually talk about energy. Okay, and when we start talking about energy and we talk about an Earth system, you sort of have to ask yourself, where is the energy coming into our system? Okay, now granted, with a planetary system like we have, the Earth, there is a lot of energy at the core of our planet. Okay, that magma, that spinning iron ball that's down the core of the planet is basically creating electric fields and things like that. But the vast amount of energy that's coming into our system is coming from what? The sun. So let's talk a few moments about how that energy is actually arriving. Okay, it comes in as a radiant energy. The sun emits electromagnetic, I can say that, radiation. It's mostly in the visible and an IR range wavelengths. So it's a short wavelength. Okay? The Earth also emits radiation, but it emits it in a long wavelength. Okay? So if you take a look at the wavelengths, this is the band of the wavelengths coming from the sun. It's basically in these micron scales here. Okay? UV, visible, IR. Okay? Earth is re-radiating some of that energy, and it's in the long wavelengths, in the meter scale. Okay? Now, if we look at that, here's the two charts at the top showing the wavelengths. If we look at that sort of in a cartoon, here's the Earth, there's the sun. Now, obviously, the Earth is not actually that large relative to the sun. Okay? The sun's bringing in shortwave radiation, sunshine. It easily passes through the atmosphere. Okay? It cuts right through. Now, the Earth, in turn, re-radiates long wavelengths. And the interesting thing about these long wavelengths is they can be easily absorbed by gases and vapors in the atmosphere. Okay? Hence the greenhouse effect. Okay? Oh, and look at that. I even put it there. Okay? Another sort of concept here is that the clouds, in turn, also decrease the net heat loss from that Earth, in essence, the greenhouse effect. Okay? So not only are we having this absorption by these greenhouse gases, we're also seeing the clouds themselves, which are water vapor, absorbing that energy as well. Okay, nothing new here. Okay, just to give you an idea what this wavelengths look like. So here's the entire spectrum, not the entire, most of the spectrum of the wavelengths. Okay, the far, near, visible, and UV. This section right in here is really those short wavelengths coming in. Okay, so we're looking at electron excitation and molecular vibration. Okay, this is sort of when you feel the sunshine on your arm or something like that. Well, that wave, that energy comes in, okay, and it starts exciting the electrons and molecules in your body, and they start vibrating, and that's what you feel the heat, right? You're not actually feeling the shortwave radiation. You're feeling the reaction of that shortwave radiation on the molecules in your body. Cool? Okay. All right, so let's get back to the Earth system here. Okay, this wavelengths that are coming in, what happens when those wavelengths actually hit the surface? What can they actually do? Or how do they get to the surface? Okay, radiation may be basically four things can happen to it. The first one is it can be transmitted. It can go all the way right through, nothing happens to it, comes right down, hits the surface. Okay, the second thing is these wavelengths can come in and they can be scattered. They can hit particles molecules that are in the atmosphere. Okay? If the wavelength hits it, it potentially will be reflected. Now, this reflection can go through a series of bouncing, okay? And we basically call this diffuse scattering, where some of it basically gets reflected back out of the system, and some of it actually gets bounced all the way down to the soil, to the ground. Okay? So you can imagine this thing is the energy is bouncing all over the place and can go a lot of different directions. The next one is it can be reflected. If it hits a surface, this is sort of the mirror effect, albedo, the wavelength hits and basically bounces off. Okay? Even if it has made it all the way down to the surface, it can hit and be reflected back out. The fourth is it can be absorbed. That energy actually makes it all the way down to an object, and that energy is then absorbed by that object. Okay? That absorbed energy is actually really important. It's only the absorbed radiation that ceases to be radiation, and this is converted to what we call sensible heat. Okay? This heat can be felt as the increase in the molecules. I mean, me talking about the sun hitting your skin and stuff like that. And it exists only in materials. This solar radiation basically heats the soil and the plant surfaces, and this heat is then dissipated from that surface throughout the system. Okay, into the soil and air, in essence, changing the temperature of those objects. Okay? Now, jargon watch, heat capacity. Okay, this is a measurement. This is a term I will talk about a little bit later, but I'm just going to give you a heads up for it. Soil temperature will change depending upon a material's heat capacity. Okay, how much heat an object needs to absorb before it changes temperature. Make sense? All right, now, if we're talking about the amount of energy that actually gets absorbed, what are the things that actually affect that absorption? Okay, the amount of radiation depends on the surface that hits the surface, depends on basically the incoming radiation rate. Now, that can be affected in a number of different ways. Okay, the first and best example of this is basically this. Okay, imagine this surface right here, this black line right here, and this black line is the surface. Okay? And the sunlight is coming straight down on that object. The energy, the wavelengths are coming straight down. Okay? Now, if I have a flat surface and it's facing it, this is basically sort of solar reflection, and I have a flat facing surface and it's coming straight down, okay, I'm going to have a maximum amount of absorption per area. Okay? Now, as that surface changes direction, the surface area is not changing, but the angle of that surface area is changing to the sunlight. The same amount of area is now going to be absorbing less energy. Does that make sense? Okay, if I'm like this, and this is my area, every spot on this surface is going to have direct sunlight. Okay? Now, that's not to say it's not going to have direct sunlight if I do this, but the amount of area is being reduced. Okay, the sun is coming, the rays are coming straight down. If I take this surface and I turn it up, you can see that I'm basically reducing that much amount of light that's actually striking that surface. Okay, so the angle of the surface to that wavelength impacts how much energy is actually going to hit that object. Right? Okay. Anything that interferes or modifies that wavelength striking the surface is going to affect how much radiation is going to get there. So, sun angle, seasonality, okay, day length, how long the day is, clouds, fog, haze, etc., the plant cover itself, okay, anything that potentially will interact with that energy before it hits the surface is going to modify the amount of energy that's going to hit that surface. Make sense? Okay. Good example of this is sort of diurnal type of stuff, but here is a really good example of soil temperature versus soil depth, and basically what you're looking at is conventional versus no tillage and 2 times a year. Okay? May versus July. Okay? This would be even better if we did this in January in the northern hemisphere, but we did it in May. Okay? No conventional tillage, basically these black dots. No tillage, the stars. The more you go that direction, the hotter the surface is, or the hotter the surface will become. Okay, so conventional tillage. Conventional tillage basically clears off all the debris off of the soil, so there's no interference. Okay, there's nothing between the soil and that light energy. Okay, so doesn't matter which one of these lines you look at. The conventional tillage versus the no-till tillage, which leaves mulch and materials above the soil, is always hotter at whatever depth. And as the sun gets higher and higher in aspect and shining straight down versus on an angle, the system gets hotter, yet you still see no-till versus conventional till. Okay? Does that make sense? So anything that's basically going to reduce the amount of energy that's coming in to strike that object. The other thing is the object itself, the reflectivity of that object, how likely it is for that material to actually absorb the material versus reflect the material. This is extremely important when you start talking about bare soils, if we're talking about soils, because you can certainly imagine that dark materials are going to absorb more energy than light materials. This is reflection, basically. This is one of the arguments, I don't know if you guys have been hearing this, but starting to make all roofs white or moving towards a white surface versus a dark surface. Does this sound familiar to anybody? Okay, and basically what you're looking at is you're trying to increase the reflectivity, so getting that energy to basically bounce off rather than to be absorbed and heat up. Okay, cool? Okay. So once that energy actually hits the ground, what happens to it? Basically, there's 4 things. 4 things preventing the soil from getting too hot, or in fact, letting the soil get hot. There's basically 4 things. There's reradiation, evaporation, conduction from that material to the air layer above, or from that soil, or conductance from that surface to the subsurface. Okay? So let's go through all 4 of these. Reradiation is basically what it sounds like. I've got energy coming in, and the object is then going to re-radiate. This is the short wave coming in and the long wave going out. Okay? You can certainly imagine, depending upon how much radiation is coming in versus re-radiation, that this could actually be heating up a system. In this scenario, the arrow represents the amount of energy that's coming in. Okay, or the arrow represents the amount of energy being moved. Okay, so if the arrow is pointing down, there's a significantly more amount. If the arrow is large, there's more energy coming in. Okay, this arrow is a lot larger than this one, so this system is heating up. Versus at night, or a frost or a dew or something like that, where the arrow compared to the reradiation, the energy is actually more energy is leaving the system than coming in. So the soil is cooling off. Imagine the nighttime. Evaporation is exactly what it sounds like. This is the heat of evaporation, the cooling of water through evaporation. Basically, it removes the heat from the soil and the air by basically the latent heat of vaporization. Okay, cools the system down. It also cools the plants, and it will also cool down wet soil surfaces. Okay, it has a little ability. If I don't have any water, it's not going to dry up. It's not going to cool up anything that's dry. Does that make sense? Does that make sense? If I don't have any water, I'm not going to have any evaporation. And if I don't have any evaporation, it's not going to work. Okay. The next one is basically conduction of that to the air. Okay? Now, this has a lot to do with the surface, the nature of that surface. The more surface area I have, the more ability I have to conduct that heat off. Does that make sense? So if I have a convoluted surface versus a flat surface, I have more surface area here, right? And if I have more surface area, this is the roughness of that material, the more surface area, the more points that I have to exchange that heat. Okay? The next thing is the gradient. Okay? It's going to be a lot faster when I have a gradient of extreme temperatures. Okay, if this is hot and this is hot, I'm not going to have a lot of exchange. But if this is hot and this is cold, there's going to be a lot of exchange. Okay? Another really good example of this is, okay, forget about hot versus cold. How about hot versus an air moving through the system? Wind. Classic example, classic experiment. They do this to kids all the time, in grade school. And they take an ice cream cone, and they have a fan, and they say, okay, now if I put this ice cream, how am I going to keep this ice cream from not melting? Which is going to be faster, if I hold it here or I put a fan on it? Okay, because everybody's used to, if I put a fan on me, I'm going to get cool, right? But what's happening there? When the fan blows on you, I'm bringing in, so it's pseudo-evaporation. I'm bringing in air, I'm blowing it across your surface area. So in essence, I'm increasing, through speed, your surface area. Okay, if I stand here and the air is still, I have a certain amount of surface area. But if I blow a fan on me, I'm exchanging the air that's around me with new air. Okay, and if this air that's around me is warmer, it's likely that the air, because I'm heating it up, right? This air is like 70 degrees and I'm 98. Okay, so I'm heating the air up around me. Okay, so if I put a fan on me, I'm going to get rid of that hotter air that's around me and introduce cooler air. All right, so let's use the ice cream cone. I put the ice cream cone out there and I ask the kids, if I have this ice cream cone, if I put the fan in front of it or I don't put the fan in front of it, which one of these scenarios is the ice cream cone going to last longer? And it's almost guaranteed every time the kid says, you put the fan on it, it's going to stay cooler. It doesn't work that way though. Why? What's happening? You actually make it melt faster. But why? So the ice cream cone has basically cooled the air around it. Okay? The air was hot and then it cooled. Okay? Because the gradient is not as much, it's going to melt slower. It's not going to not melt, but it's going to melt slower. But what happens when I put that fan on it? I drive the cool air away from the ice cream cone and introduce more hot air, which means the gradient is more extreme, which means the ice cream is going to melt faster because it's cooling the air around it. Does that make sense? Conductance to air. Go.
What's the difference between reradiation and conduction to air?
The one is a temperature and one is a wavelength. Long wavelength versus sensible heat. Okay? All right, the same thing applies to, I can transfer heat upward into the air, but I can also transfer heat downward, right? Okay, I heat a surface over here, that heat is going to migrate through the material. Okay? So this occurs only when the soil surface is hotter than the subsurface. And it reverses when that temperature profile switches. So if it gets hot down below and the surface starts getting cooler, the energy is going to be transferred upward. Does that make sense? Yeah? Okay. Questions so far? Which brings us back to this concept of heat capacity. Okay? Heat capacity is basically a measurement of how much energy or how much heat an object needs to absorb before it can change temperature. Okay? We measure it basically in 1 degree Celsius, so it's usually expressed as a bulk volume. Okay, I have a volume of material, you know, a cubic centimeter of material. How much energy does it take to be converted in? And this is converted to a temperature. This is the exact same measurement as calories, by the way. Okay, 1 calorie, I think I have it in here. The specific heat of water, a little bit differently, but basically 1 calorie per gram. Okay? So it takes 1 calorie of energy to heat up 1 gram of water 1 degree. Okay? Okay, this is the amount of heat capacity the water has. Okay? It increases with bulk density. You can certainly imagine as a material gets denser and denser and denser, same material but you densify it, if that's a word, it's going to increase the amount of energy that you need to heat that object up. Does that make sense? There's more material there in the same volume. Okay? At constant bulk density, it will increase with water content. Now we're talking about soils here, so remember we're talking about this whole volume. There's a lot of pore space in that volume. So if I put other materials into this given volume, and it doesn't have to be water, it could be any kind of liquid or any kind of mixture of material, you know, as I start a volume and I start adding other things into it, those other things are going to be adding their specific heats as well. And so my volume is going to take more energy to heat up. Okay, so let's go back to the soil. I have a volume of soil and it's bone dry. It's going to take a certain amount of heat to heat it up, a certain amount of energy to heat it up. But if I add water to it, it's actually going to take more energy to heat up that same volume. Right? Questions? Okay. The specific heat is the heat capacity expressed per that unit mass, i.e. the calorie in water. Okay? The specific heat of minerals is about 0.2 versus 1 calorie for water to get it to move up 1 degree. Okay? The results of this are, if you think about a soil with a large heat capacity that's like a dense or a wet soil, if they are in the same location as a dry soil that's less dense, which soil is going to dramatically change temperature? If it takes more energy to heat up the dense soil than it does to heat up the dry soil, or the less dense soil, which soil is going to change temperatures more dramatically? The one that takes the less energy, the less dense one, the dry soil. Does that make sense? Yeah? Okay. The heat capacity is very dependent, therefore, so think about this. That heat dependency, or that heat capacity, is very dependent on the soil water content then. And it's also very dependent on the total heat capacity of that material. So I have a single material and then I add more material. Okay, if I have one material, let's take a step back. I have 2 different materials. One has a larger heat capacity than the other, i.e. it takes more energy to heat it up. Okay, and then I add water to both of those systems. Water is just going to attenuate the heat change. It's just going to make it longer or harder. It's going to make it more, I'm going to need more energy to heat these things up. So the water in both cases has the same amount of heat capacity, and if I add it to a system that has less heat capacity versus one that has more heat capacity, I'm just going to make both of them go up, but the one that has less heat capacity, the material that we started with that has less heat capacity, is still going to have less heat capacity than the other one in a wet system. Does that make sense? Yes, okay. The result of this is, well, okay, I put these in here just so you can sort of see some comparisons. Heat capacity of sand is 0.3. Heat capacity of water is 1. Heat capacity of air, because there's not very much stuff in here, is 0.003. Okay, just to give you sort of an image of this. The result is, when you start adding up the heat capacity, you basically have to add up all three, the solid, the liquid, and the gas, put them together into that volume, and that is your heat capacity for that volume. Okay, the gist of this, though, is because this heat capacity is so low, you really just have to add these two together to get the heat capacity of a soil. Make sense? Okay, now let's take a stop. Let's take a moment here and think about heating. Okay, who here has a house or an apartment or a dormitory that's basically heated by forced hot air? It's hot air that's being driven through your system. Okay, now who here has a system that's being heated by water? Either radiants or radiators or radiant floors or something like that. Okay, now which one of those systems does it take more energy to actually heat up the object that's doing the heating for everything else? Okay, so basically we have air versus water. Which one of those takes more energy to heat up? Water. Okay, now we haven't talked about this yet, but think about this. Which of those systems is actually more efficient? Water. Why? It takes longer to cool down, but the other really kind of cool thing, and we haven't talked about it yet, is this is how much energy it takes to heat something up. But this object, in turn, can heat other things up by transferring that energy. And that term is what we call heat conductance. This is heat capacity. The capacity, I mean, how much energy it takes to actually heat something up. But once you've got it heated up, what happens to it? Well, it transfers that energy to other things, and that term is heat conductance. How does that heat actually move through the soil? Okay, we've got the surface of the soil, we shine light on it, the sunlight, it heats it up. Okay, we understand why it heats up. Well, how does that actually heat get transferred? Okay, all right. This conduction is basically based on what we call the Fourier's equation or Fourier's law. Okay, and this is the equation down here, but let's explain the equation by actually looking at a block. Okay, here's a material, okay, and it's getting heated up this way. Okay, how effective this thing is to transferring the heat basically is a measurement of how conductive that material is, the effectiveness of that heat to conduct, the area that's actually conducting, okay, how big is this object, and how much surface area this object has with the object that it is heating up, okay, and the driving force, i.e. the gradient. If this is cold on this side and hot on this side versus hot on this side and hot on this side, you can certainly imagine the conductance is going to be a lot slower in the hot versus hot system versus the hot versus cold system. Okay? That law is the amount of heat crossing a certain area in time. Okay? So heat flow, we measure it as a Q, but basically it is a measurement of change in heat over time. Okay? A is the cross-sectional area. That's the area that this is moving through. Okay? K is the conductivity, how effective it is as a heat conductor over a change in time, over a change in distance. Okay? Questions? K is the thing that we really should be concerned about right now. Okay? We can understand if I have a temperature gradient, that makes sense. And we can certainly imagine that to contact the size of the object is going to have a huge impact. Okay? But let's think about how fast this object can actually conduct that heat. Okay? And it really depends on the soil's water content. This is a particle, an individual solid mineral. Okay? The heat moving from the top through the object, it's pretty fast. Nice contact points, pretty consistent material, moves through. Okay? The same volume of material, but you actually have individual particles. You'll note that the contact, the transfer points, are just where those two pieces are touching each other. So I am limiting the flow of energy, or the flow of heat. This system, the system is not limited by contact points. The whole thing is a contact point. This one, the same volume, I have very limited transfer. Okay, now with a soil system, yes, we have solid particles, but we're generally talking about lots of little particles in a volume. Now, let's take that same system that we have here and we add water to it. Well, what happens? The water now is a player. The water now can conduct. The contact points have dramatically increased. Okay? The water moves through and transfers that water, or transfers that heat. Okay? Now, if we actually look at the particles themselves, this basically means that sand is the best, clay is in the middle, peat is the worst for conducting this energy. Now, think about this. Why? Why would we think that? Sand versus clay versus peat. Certainly the sand and clay we can sort of imagine over the peat. Well, why? Why is it better than in peat? The solid mineral materials. Let's look at our volume. I got one volume. I start packing it up. Do you want to say something? No? Go ahead. If I have a given volume and I fill it with sand versus peat, which of these is going to have more contact points to transfer that energy? The sand will. And you guys have, hopefully you guys have all picked up peat. You see how light it is, how much pore space is in there? Okay? And that in essence is what they're talking about here. How much contact, how much material is actually conducting this material, conducting the heat. Here's a couple of examples here. We're basically looking at quartz versus dry sand versus wet sand versus water versus air. Quartz, really high conductance. Have you guys been on the beach in the summertime, under the sun? What do your feet feel like? They're pretty hot. Okay, they're conducting that heat to the bottom of your feet. Okay, what happens when you get into the wet sand? Cools down. It's still pretty good at conducting that heat, but not as good as that packed sand around you. Okay, water versus air. The interesting thing here, if you note, is that if we went back and took a look at the thermal capacity of water is pretty high compared to solid material, but the thermal conductivity of water compared to solid material is a lot lower. Okay, of course it's a lot higher than air. Okay, so let's put these two together. We have thermal capacity and heat capacity. Basically the combination of the two of them determine the shape of the temperature curves, or the thermal temperature profiles through a soil. Okay, so here's temperature, and this is time, noon, noon, noon. This line right here represents 25 centimeters down. This line right here represents 1 centimeter. Okay? Now I pose two questions here. The first is, when will heat flow be most rapid? And the next one is, where will heat flow be most rapid? Same location in essence, and time. They basically correspond to each other. Okay, if I'm moving from high temperatures to low temperature, you certainly should look for the high points temperature-wise, and then look for the cool points, because that's where the energy is going to be transferring. Okay, so let's imagine this one, noon at 1 centimeter. Where's the heat moving? Some of it's going to be coming back off, but where's the heat moving? It's going to be moving downward, right? Dramatic, well, relative to this profile, the dramatic delta in the temperatures is right here. Okay? This material is heating that below. Below is heating up, but look where its hottest point is. At midnight. 1 centimeter, its coolest point is at midnight. What's going to be, where's the temperature going to be going now? It's going to be going from 25 centimeters down to 1 centimeter. Or up to 1 centimeter, basically, I should say. Okay, does that make sense? So we've literally inverted the heat profile just because we've changed the temperature at the surface. Well, what's happening at the surface? At noon, the sun's shining. At midnight, the Earth is re-radiating and getting rid of all that temperature. Does that make sense? Questions? So the when is here. The where is here. Does that make sense? Let's keep going. Okay? This is out of your book, and basically what you're looking at here is temperature in Celsius going up here and the months of the year. You have a variety of different different temp depths here. You have basically 7.5 centimeters, 30 centimeters, and 90 centimeters. The black dot here basically represents the air. The black dots, that line basically represents the air temperature. Okay? Air temperature, January, December, pretty cold. June, July, August, warm. Okay? We can see that reflected on the soil surface, which is the 7.5, this dark solid line. It basically mimics the air temperature. But you'll note that the 30 centimeters and 90 centimeters, the peak is here, the peak is here, the peak is here. So what's happening? The heat is being transferred down, but it takes a while for that profile to get transferred down. So it's delayed. Okay? And then, someplace down in here, in September, October, we have an inversion. Okay? The surface temperature is matching that air temperature and dropping. The peaks are starting to drop down because they're starting to transfer their heat back up to the surface. But even in December, yes, they've gotten a lot colder, but even in December, they're fairly warm, certainly relative to the air temperature and the surface. So a seasonal change. Okay, here this one so far we've seen is the daily change. Now we're starting to see seasonal changes. Okay, now how about we look at that through the whole year and we basically look at those curves. Okay, here's the soil surface down to 300 centimeters, 3 meters. Okay, you can basically look at these curves. We'll start in January, cold surfaces, warmer subsurface. January, then we get March. Sun starts coming out. Okay, that's the season of mud around here, right? Starts warming up at the surface, but you'll notice that the soil is actually getting colder down here. The heat's still being transferred up, so it's getting cooler. March, May, right here, more sunlight coming in. Sunlight, the energy is starting to be transferred down. You see at this point, we're looking almost like a straight line up and down. Yeah, there's still a little bit more energy going upward, but once we get to this point, you can see the energy starting to go down, and that's why the temperature starts coming up. Okay, May, July, really hot. Energy transfer here and here, all heating everything up. It's hot here, transferring it down, moving it forward this way. Okay, May, June, July, and then we start having September. Okay, surface starts cooling down, bottom is still heating up. Okay, this is still colder than that, so there's certainly energy being transferred down. September, November, right here, this line right here, we start seeing the top getting really cold, energy is being transferred from below to up, and so as a result, we start seeing this march back down, and we'll ultimately get right back to January. Does that make sense? We have heat moving downward when the surface is hot. We have heat moving upward when the surface is cold. All right, it's not just about seasonality, it's also about management. Okay, here is basically soil temperatures in a clear cut. Here's soil depth, surface to 28 inches. You're basically looking harvested and bedded versus an uncut forest. Wait a minute, no, I did that wrong. This is the uncut forest. This is the harvested and bedded, and this is the clear cut. Yes. Yes, okay. So, uncut forest, soil depth, cool soils compared to a harvested and bedded. Basically, this means it's not only it's been harvested, but everything's been stripped out. So all the recut material, all the scrap stuff, it's been taken out. Okay? So just look at the comparison of these two. Well, what's going on? This is not a seasonal thing. This is a management effect. What's the management effect? If I've taken the trees out and I've taken all the cover out, I've got a lot more energy actually hitting the soil. And if I got more energy hitting the soil, it's going to heat it up even more, and we're going to see that transfer moving down. Make sense? So a management effect. How about a much even more dramatic management effect? Let's talk about mulching. Okay? Classic example here. We've got the temperature, basically the 0 point here, versus negative versus positive, versus a bare soil. This soil has a leaf mulch in it. Air temperature, soil temperature. This line right here represents the temperature line. Okay, and you'll note that at depth, they're basically the same, and at the surface, the air temperature is the same. The change is really in here. Well, what's going on? This one, in fact, has snow on the surface. This one doesn't. Well, look at where the temperature line hits the surface here. In this case, right here, it's at 1 degrees. In this case, when it hits the surface, it's at -1. Well, what's happening? This surface is definitely warmer than this surface. So what direction is the heat going? It's going up, all right? So it hits here, and it's hitting here at 1 degree Celsius because the heat's being transferred up here. Certainly you could make the argument that this soil is going to cool down a lot faster, okay? Because it's 1 degree, the snow melts, and I don't have any snow there. What's happening here, though? When it hits the surface, it's not at 1 degree, it's at 3 degrees. The energy there is then being transferred to this mulch zone, these leaves. And this is where thermal conductance comes into play. This is like a peat versus a mineral. The leaves, there's a lot of air in here. There's a lot of pores. It doesn't take a lot of energy to heat up the air, but that air doesn't conduct it very well. And the surfaces of the leaves that are touching each other, they're very limited. So the transfer of heat through the leaves is very, very slow. And so as a result, this zone in here, look at the change in temperature here versus the change in temperature here. This is basically acting like a blanket. Warm body down here, cool air up here. The blanket serves to keep the insulation or slowing that transfer of hot air out of the system. Cool? Questions? Nope. Okay. All right, so we've talked about variation in sort of the daytime, the seasonality. We've talked about management issues. Why don't we actually talk about some variations in soil climate based on positions of the world? Okay, in the higher latitudes, mean soil temperatures will shift seasonally, which makes sense. I mean, we have seasons. It's colder, warmer, winter, summer. Okay, and then we'll also have very dramatic diurnal variations superimposed on top of this. Okay. We have longer days in the summertime, shorter days in the winter. Okay? So we're going to have a diurnal effect, not just a temperature effect from our latitude. Okay? The tropics, the sun angle is always pretty high. The day length is always pretty consistent. Okay? As a result, the soil climate is not characterized by heat because of moderation of a lot of things, but also I have a moderation of the day length, but I also have a lot more cloud cover down there, and I also, if you look at the planet and you look at where the tropics are dominated, the whole planet, the tropical zones, the latitudes are dominated by oceans. And the oceans, it takes a lot of energy to heat up water. Once they're heated up, they'll stay hot for a long period of time. But what that's going to do is it's going to moderate the soil climates in these tropical zones. Okay? It's never going to get super hot, the soils, and it's never going to get super cold, because the energy of that system is not going to change as dramatically as it would in the higher latitudes, whether you're in the North America or in northern latitudes or the southern latitudes. Now you also have local variations, and these are sort of, I've been premising these as management, but It depends on the aspect, that slope angle. Remember the surface area being hit by the light, the water content of that soil, as well as the cover. So if I have a bare soil versus a mulch soil versus a plant cover, this line represents the temperature gradients, okay? And here's the line for the temperature gradient. All right, so let me ask a question. At this point, we should be able to answer. Why do wet soils get less hot than dry soils? Evaporation? Conductivity? High heat specific capacity. It takes more energy to heat them up. When I have a wet system, it's going to evaporate. And wet systems are much better at conducting that heat than a dry system. All of those basically mean that these soils are going to be less variable. Cool? Questions? All right, let's talk about management. Let's get back to management. Okay, management of soil temperature. Now, we basically, if you want to talk about management of soil temperature, you're going to basically want to do two things. Well, actually three potentially. One is you're going to want to raise the temperature, or you're going to want to lower the temperature, or you basically want to maintain the temperature. Okay, so maintaining the temperature is basically reducing the amount of energy moving into the system and or making the system more resilient to that energy change, i.e. a wet soil versus a dry soil. Okay, so what do we want to do if we want to raise the temperature? Okay, well, why would we want to do this? Certainly you can think of some spring examples. Okay, the first one right here. In the springtime, I want to raise my soil temperature. So certainly if I'm in agriculture. Why do I want to raise it? Because seed germination, seeds need a certain temperature for them to germinate. Okay, so if I raise the temperature into their germination range, I'll have better germination. Okay, I also may need to have a certain temperature range for the root growth. Certain trees, certain plants will not grow when the soil is too cold. It makes sense to them. Okay, it's just sort of a controller. Okay, so what kind of methods do we have actually to heat up the soil? Well, we can change the specific heat. Okay, or we can change the amount of energy that hits the system. The first one is let's change the amount of energy that hits the system. Let's remove all the cover so we have the maximum amount of sunlight hitting the soil. Does that make sense? Anything that's going to get in the way of that short wavelengths hitting the ground is going to reduce the amount of energy that's hitting the soil. It's going to reduce the amount of heat. Okay, so let's get rid of that stuff. If I can keep my soils dry, I reduce the amount of energy that I actually need to heat things up. Okay, if I have a wet waterlogged soil, it's going to take a lot longer to heat up than a dry soil. Does that make sense? Okay. I want to mulch it, but I want to use a specific kind of mulch. I want to have a transparent mulch, a mulch that's not going to prevent the long wavelengths from going into the ground, but is going to prevent the short wavelengths from re-radiating. Basically, I want to put a greenhouse in, basically making a pseudo greenhouse effect. Black plastic also, I can also heat up the material by increasing the amount of absorption. If I have a dark soil versus a light soil, if I reduce the amount of albedo, if I suck in more material, and that's the idea of using a black plastic versus a clear plastic. Use a black plastic, more heat, it absorbs more. Okay, granted, I still have to transfer that heat from the mulch to the soil, but if I heat it up enough, I can overcome that conductivity break, that issue with conductivity. Does that make sense? Questions? This is how I want to heat the system up. Okay, what happens though in the middle of the summer? I don't want my soils to be superheated because then I'm going to start stressing my plants and the organisms that are in there. So what kind of stresses or what kind of management things could you actually use to lower the temperature? Any thoughts here? I got some good examples. How about this one? Exposed soils, in parentheses, brief. I expose my soil, I'm now opening up to direct contact from the radiation, right? So that probably is not a great idea. But if you think about it, you can think about when the radiation is at its smallest and re-radiation is at its most. If I was going to do this exposed soil, when would I want to do it? Somebody said it. At nighttime. Make sense? Okay, how about some other type of strategies? I mean, we can certainly do this with greenhouse pots. I mean, it's probably a lot harder to do if you've got a whole cornfield. Okay, how about some other ideas? This is the classic greenhouse one, but we use a shading device. Okay, but there's a lot of different types of shading devices out there. Okay, when we say shading device, most people think of like an umbrella or cover or something like that. But how about a vegetative cover? I start getting biomass above my soil. That starts interfering with the radiation coming into my soil, and I'm reducing the amount of heating of my soil. Make sense? Okay, how about mulching with straw? Putting a mulch out there. Yes, I showed mulch in the cold system, but this mulch would invert this line in the warm system. Does anybody have a garden that they mulch? Okay, how often do you mulch? And when do you mulch? You mulch in the spring? When do you mulch?
Mostly in the autumn and then some in the spring.
Sometimes in the autumn, sometimes in the spring. What do you guys do in the summertime? Do you leave the mulch on, take it off? What do you do? A lot of people do it in late June, late spring. They mulch and then they pull it off for a period in the fall and then they mulch it again. Does this sound familiar to anybody? Okay, let's think about this. Okay, springtime hits. What do I want my soils to do? I want them to dry and I want them to warm up. Okay, is that the time to have mulch on my soils? No. Okay, once they dry and start warming up, okay, and I've got the soils up to heat, is that the time to put mulch on? Okay, so late spring, early summer. Okay, summertime rolls in, it gets really hot. Okay, you want the mulch in there because it's climate control. It's not just temperature, it also modifies moisture. It holds more moisture when you have mulch in there. Okay, but late summer, early fall. Okay, start thinking about what's going on now. Okay, certainly when I have tender plants or plants that are going to die off, I don't have to worry about it too much. On the other hand, let's think about what happens often in the fall around, and certainly around here. We have Indian summers, okay, where the climate gets really cold, and then for a couple weeks we'll have summer again. Okay, we had March, 84 degrees in March. What was the last? It's crazy. Okay, what should we do? When the system starts getting cold and your plant starts senescing, it actually makes sense to take the mulch off. Let the soils get cold. Send the message to the plants that winter is coming. Start shutting down, storing up for the wintertime. Okay? Once the plants shut down, what should you do? Put the mulch back on. Why? If I don't, Indian summer hits, those soils start heating up. It tricks the plants into thinking that summer's coming. When in reality, in 2 weeks, they're about to get, I want to say toasted, but that's not exact. They're about to get frozen. Now, if I let them cool down, and then I put the mulch back on, when I get that Indian summer, that mulch is going to actually keep the soil cool. And the plants won't be fooled into thinking summer's coming. Does that make sense? Okay, then the middle of the wintertime, or the end of the wintertime, beginning of spring, what do I want to do? I want to heat my soils up again, so that's when I take my mulch off. Okay, get the soils drier, get the soils warm, and then I put the mulch back on when I got them to the temperature I want. Does that make sense? Let's go back down to this slide. I totally missed it. All right, that was actually the last slide anyway. Okay, questions? All right, we are going to go out to the field today, so be prepared. Okay, otherwise, be free. Have a great day, guys.